Hey everyone, and welcome back to another video with your boy Hubby here. And today we are going to solve an integral using the complex analysis like we said it in the previous video. And we have the integral I equals to 0 to infinite x times sine x over x square plus 1 dx. To solve using the complex analysis, first we need to change the boundaries as half minus infinite to plus infinite x sine x over x square plus 1 dx. Well, now it's time for us to use the imaginary part. Well, this is half minus infinite to infinite x times the imaginary part of e to the power I times x over x square plus 1 dx. Well, we know that the e to ix is actually cosine of x plus I times sine x. So we have this is the real part of it and this is the imaginary part of it. So we can use imaginary part of e to the ix to the sine x. Now we need to name this as a function. F of z is equals to z times, we need to change every x element to the z part. So we have x here, so it will become z, and we have e to the I z over z square plus 1. Well, we can see that in the complex plan we have negative r to plus r will have a curve C. So for poles we'll have z square plus 1 equals 0, where we get z equals to plus or minus I. Well, we can now see that z equals to I lies inside the curve C, because we'll have the imaginary part here, but the minus I lies outside, so we don't need to worry about this part. So we'll have the integral here, which is the counter integral of f of z dz is equals to negative r to r f of z dz plus the curve we have here. Terribly sorry about that, which is c1 f of z dz. So first let me name this as c1. So okay, this c means the counter and this is the curve we have there. So let's find the residue first. The residue of f of z when z equals to I, we have limit z tends to I z minus I times z times e to the iz over z minus I times z plus I. Let's move on to page number 2. So we have the limit. This part and this part actually cancel each other out, so we are finally left with I times e to the negative 1 over z plus I, means it's actually 2i, so we can cancel these I together, so we'll finally left with 1 over 2 times e. Well, by Cauchy's residue theorem, we have by Cauchy's residue theorem, the contour integral of f of z dz is actually equals to 2 times pi times I into the sum of residues. Well, now we have only one, which is 1 over 2 times e. So we have here pi I over e. Now by Cauchy's lemma, by Cauchy's lemma, we have here the curve f of z dz equals to 0 as r approaches to infinite. So the integral now we have here is the counter integral of f of z dz. This is actually the curve, I'm terribly sorry about that, is equals to negative r to r f of z dz plus the curve f of z dz. For the counter integral we have pi times I over e is equals to, now when the r approaches infinite we'll have minus infinite to infinite f of z dz plus 0. So let's move on to page number 3. So we have here now applying our f of z there, so we'll have pi I over e is equals to minus infinite over infinite z times e to the I z over z square plus 1 dz. Well, now we can actually see that this is the required integral, but with an imaginary part. The required part integral is I equals to 0 to infinite x times sine x over x square plus 1 dx. Well, this actually we changed into half minus infinite to infinite x times imaginary part of e to the ix over x square plus 1. Don't forget the dx. Well, for this part actually we can take the imaginary part outside, so the required integral will become minus infinite to infinite x times e to the ix over x square plus 1 dx. I am terribly sorry about that. It's actually e to the ix. Well, you can see that this part and this part are actually the same. So the only half is missing. So we'll have here pi I over 2e will become half negative infinite to infinite z times e to the iz over z square plus 1 dz. Well, these are just dummy variables. When z tends to x, we'll have pi I over 2e is equals to 1 over 2 negative infinite to infinite x times e to the ix over x square plus 1 dx. Well, okay, cool. Now we have to take the imaginary part both sides. So it will become the imaginary part of pi I over 2e is actually pi over 2e. So the required integral's answer will become I equals to 0 to infinite x times sine x over x square plus 1 dx is equals to pi over 2e. And that's the answer, which look pretty gorgeous here, which involves pi and Euler's constant. And yeah, that's it for tonight, guys, and we'll find another type of integral in another video coming next weekend. And until then, bye bye from your boy Abhi here, and please don't forget to subscribe my channel. Thank you.